Welcome to the Science of Beers podcast with me, Michael McGee. Talking science and drinking beers with researchers down at the pub. So join us with a brew and let's cheers to science. This is the 7th episode in the 3rd season of the Science of Beers podcast. This season is made in collaboration with our friends at the Danish Institute for Advanced Study. Our guest today is the founder of that institute. Francesco Cenino is Professor of Theoretical Physics at another group that he founded and now directs, the Centre for Cosmology and Particle Physics Phenomenology, otherwise known as CP³-Origins, at the University of Southern Denmark. Before his current role, Francesco has been working at the Niels Bohr Institute. He has been working at Yale University. He's been working at the Large Hadron Collider at CERN. And he has not one, but 2 PhDs. So I really can't think of anybody better to sit down with a beer and ask, what is the universe made of? And we do that by looking at a beer and seeing what secrets of the universe are held in the glass. It was really clear for me that Francesco's driven by the fun of curiosity and a genuine love for the beauty of nature and German Weissbier. We get into a lot of different subtopics in the history of the universe, so you'll be able to see in the description a timestamp for all the different topics, and you'll be able to see some links as well to some talks that Francesco has given before at the Danish Institute for Advanced Study. If you like what you hear, go back and listen to the rest of the season. We cover a different topic each episode. Also, tell a friend about the podcast. Give us a review, especially if you're listening on iTunes, and share the podcast. I am your host, Michael McGee. Cheers to science. Francesco, thank you very much for joining me for a glass of delicious German Weissbier from Bavaria. Skål.
Skål.
Refreshing as it is on this beautiful warm day. So, you're a theoretical physicist, is that right, Francesco?
Yes.
Yes?
Yes, and it's so cool. Yeah. It couldn't do anything which is more cool than that.
There's rock star and then there's theoretical physicist.
Right. As one friend of mine used to say, it's like a rock star without the groupies.
So your job is to think about how the universe works.
Yeah, maybe just not to think about it. They would probably won't pay us if we just think.
Yeah.
Try to figure it out and try to write it down. And once you understand things, then you can also manipulate them. And you can, for example, transform them into engineering. And then our sister sciences like engineering, chemistry, and so forth, so on, they can actually use what we do to then do amazing things in the world, like GPS.
GPS, so
global position system.
So are you talking about how quantum physics links in with GPS?
General relativity, yeah. If we're not for Einstein, we wouldn't be able to know where we are on Earth.
Please explain.
Yes, I mean, the global position system uses basically general relativity to be able to accurately tell us where we are on Earth. So only took 100 years from the theory to be able then to construct instruments to be able to use the theory accurately. So we do need to correct for general relativity corrections to be able to get at the right location on Earth. So from this to your iPhone.
Is that because our phones in our pockets on Earth experience gravity more than the satellites?
No. It's just that in order to make sure that we can locate you or locate me, so precisely we need to be through satellites. The satellites need to be synchronized with an extreme accuracy, both their geolocation and the timing. And to do that, you need to correct for their precise position that is also affected by gravity.
Would a clock on a satellite experience time differently than a clock in my pocket?
Well, I would say that anything that moves compared to you, right, in that reference frame will actually have display and go with you will have to synchronize with you, right? And so that actually requires special relativity in that case, not general relativity to this extent. So you need to synchronize properly. and since it's relative, their time will be different than yours. So you have to communicate and correct it for that. Of course, for anything you do on Earth, like, if you're going on your bike, then you don't care so much. The difference will be so tiny. Mm-hmm. But because anything cannot travel faster than the speed of light, we have to adjust for that.
So there's real-life implementations for
immense, yeah. I mean,
for example,
imagine what can we do with the laws of nature we have not yet understood.
Well, this is the thing, I'm a biologist, but I would be interested.
I'm really sorry for you.
I'm really interested in reading about physics and trying to wrap my head around it, which I hope you're going to be able to help me today with. Yeah. But some of the things that really don't really I can't compute. Yes. Make this world go round. They're responsible for the electronics that we've got and GPS, as you said. But I have a special challenge for you today, Francesco.
Yes. Please, hit me.
It's a Science and Beers podcast. Let's work in the beers with the science here.
Yes.
Can we zoom in on this delicious glass of German Weiss beer?
Please, let's do that.
So, allow me to start.
Yes.
So, I'm looking at this beautiful golden liquid with a creamy white top, and we're going to really zone in there into the actual molecules, the molecules that are giving us a little buzz at the moment.
Yes.
The ethanol.
Yes.
So that's a molecule with 3 different kinds of atoms: carbon, hydrogen, and oxygen, linked together through covalent bonds. So they're sharing electrons. I know that exists.
Yes.
I know that happens, but can you explain to me what's going on there? How do they stick together, and how do electrons and protons work together?
Okay, so now this is basically many different layers, right?
Yes.
Of physics and many layers of science that we have to cover. So, the question is, how do we need to explain all of that? Or we just want to understand the fundamental forces that actually led to the atoms in the first place, and even before the atoms, to the nuclei inside the atom. So the quantum world, the one that you and I have to use to explain the ethanol as a photon, is right now really old stuff, right? It's about over 100 years old. So that more or less we understand more than less at the quantum level, and this has to do with the quantum world, when you have actually understood how electrons can be stuck to the nuclei and make atoms. And then atoms are stable because of the fact that the orbits around the nuclei of the electrons are quantized. So otherwise they will actually radiate and fall on the nucleus. Right? So Bohr told us that this empirically, that these electrons cannot really be at arbitrary distances from the nuclei. They need to be at certain distances. And then when you have different atoms together, the electrons like to share themselves with the other atoms. And through this sharing, which has to do with the electromagnetic force, they effectively are able to make bigger atoms, which eventually we call molecules after a while. And they make chemical bonds and so forth, so on. But they're all based on quantum and electrodynamics, the same force that also provides the electricity.
Yeah. Could you explain what is that force that's keeping the electron from getting closer to the proton?
So if you actually just have an electron and a proton, and they stand like that, the electron actually will fall on the proton. The reason why it doesn't fall is because the electron, when the atom has been made, also has a little momentum in the direction orthogonal to the direction that will go directly to the nucleus. So what actually does not allow the electron to fall is, again, classically the atom would be stable. But quantum mechanics, but because classically would not be stable. The electron going around will radiate and fall on the nucleus. Now, quantum mechanics prevents that to happen by saying that, again, the electron can both be at the same time a wave and a particle. And now this is one of the, when you say that, people goes like, what? Why we can do that? Wave of what? clearly not a wave of beer, not a wave of fluid. It's a wave of probability. So we give up, when we get to the quantum world, in the explaining everything in terms of a single point-like object, but we say that we can at best provide the probability with which the electron is there. So we're going to say that we have a wave of probabilities. And now if you have waves, you probably have seen that when you have waves, if you put them on a pond, right, they actually make nodes at the end of the pond, or makes actually maximum and minimum. And when you put on a sphere, like it could be around the atom, only certain frequencies are allowed. So not all of them are allowed. Therefore, this probability only certain type of distances that you can have from the nucleus, and this is actually the basics of quantum mechanics. So when you actually understand that at that level you're not allowed to describe the electron just as a point-like particle, but as a wave.
So an electron behaves sometimes like a particle and sometimes like a wave. I know that that's also true for light. It behaves like a wave or a photon.
Yes, yeah.
So how does light, white light, interact with this glass of beer? Because I'm imagining there's white light coming and hitting the beer, and it's there's only a beautiful golden color coming back.
Yes.
Back to me. What's going on then at the atomic level?
So when actually the light comes to the glass, in this case to the molecules of the beer, it will actually make the electron jump from certain from their equilibrium state to some high excited state. What you observe is then this electron falling back and giving back the light they have absorbed. And they only absorb the light that is actually then the color you see. So you see only the light that have been re-emitted by the electrons once they have been excited. So not all the spectrum of light is absorbed by every single molecule or every single atom. Only a specific one, the one which make them jump to, if you can imagine pictorially, to some larger distances. Then they will go back and they'll emit their particular type of light. That's, a larger stand gives us different frequencies that you see.
So the beer is absorbing the golden frequency and then re-emitting that golden frequency again. Exactly. And this microphone in front of me is absorbing the grey and then re-emitting that again.
Exactly.
What about the other wavelengths of light?
So they will all affect other materials, other particles, other free particles which are not, for example, bound. So it depends exactly what you're impinging onto. I mean, it's a property of the material at this point. That's why you can study the materials, right? It's exactly the way we study materials. So we do what a 3-year-old kid would do. You throw at them stuff and see how they react. So the same we're doing with light and what we have around us. Yeah. So you actually know that, and then you can also extrapolate. Of course, you can have different type of frequencies. You can have entire spectrum of frequencies, but some atoms only react to a certain frequency. That's also the way we know what stars are made of, because they only emit light coming from the material they're made of.
Because they're emitting light that tells you about the stars.
Exactly. We know all the elements that are in stars. We can look at the sun and see what the sun is made of by actually looking at the spectrum of light coming from the sun.
So the spectrum of light coming from our sun in our solar system is different from the spectrum of light coming from a different
Absolutely,
star.
Yeah. Depending on what the star is made of, right?
Okay.
Yeah.
And so what is our sun made of?
Well, our star is a red giant, so actually it's not a very powerful one, and why would be burned already. And actually is as each single star starts basically with like an engine, start basically burning up elements. So it starts with the hydrogen that makes helium. So you have to think about it, that you have gas, and then gas likes to collapse. Because of gravitational, through gravitational force. So it likes to collapse. But as it tries to collapse, at this point, the atom wins the electromagnetic repulsion and gets actually squeezed very much against each other. think about hydrogen. Hydrogen is basically one proton, one neutron, and one electron. So, but when that happens, so this actually, at this point, the nuclei gets closer to each other, and they start fusing. They're fusing and making heavier and heavier atom, in this case helium. So, and when that happens, actually, the fusion process keeps the star in equilibrium, thermodynamic equilibrium. On one side, gravity likes to push. On the other end, the gravitation, the pressure, the thermal pressure coming from burning up keeps the star from collapsing. So the fuel keeps actually burning. More hydrogen become helium. At one point, everything's helium, and so the star collapses because there is nothing to burn anymore. But at this point, the helium starts getting close to each other. It makes another cycle, and then it starts with heavier elements like carbon, oxygen, so forth, so on. So literally, we are stardust because we came from the stars that exploded. In particular, we think we come from supernovae.
And that's us, but that also refers to the carbon, the hydrogen, and the oxygen in this molecule of ethanol that's giving us the buzz.
Yeah, everything, exactly. Everything here, from what gives you the buzz to what gives you the sound, gives basically our own existence, is due to the fact that the stars have metabolized different elements and created heavier elements. You can also ask what is the heaviest element a star can produce.
Yes.
And it's iron. That's why we know that we are very late in the stage of the universe stage, because Earth is has a lot of iron in it. So we came from a very an explosion, presumably, of a supernova type 2. And that actually is once they burn everything, got up to the iron, there's nothing to burn anymore. Then the star is doomed to collapse and to actually burst after the collapse, and the elements are thrown out in the universe, and eventually they start, because gravity likes to keep things together again, they start forming planets, start forming other objects. And we are actually, the solar system came from, we are actually, again, very young in the sense we just, late in the process of the universe being formed, but we are actually recycling old elements.
So the elements that are heavier than iron, then, they were formed in the force of the explosion of the star, the supernova. There
is nothing that is that we can right now make which is heavier than iron. Iron is the heaviest element nature can form. Yes, the most absolute is the heaviest stable element that a star can form.
So what about the uranium, for example? The things
human made, yeah.
The things that have more protons and neutrons in the core.
Yes.
So there's lots of elements.
For example, cesium, 132, so for some, they're actually all, and radium. I mean, they actually were all produced in a very smaller amount, and they actually humans have made a great deal of those. There are other elements that can be formed, right? So it's not a problem to actually go beyond that.
But they were formed in the supernova blast?
No.
Okay.
No.
Right.
I mean, there might be, depends on it's easy. The cycle of the stars actually ends with iron.
Yeah.
So that's actually why we know whether, if you discover a new civilization, right? How do you discover it? You could also discover they've been, making elements the stars don't make.
Mm-hmm. And you'll be able to see this with light, because each element has its own light signature.
Yes, absolutely, yeah.
And the light signature is to do with how the electrons are formed around the nucleus.
Yes, exactly.
of the atom.
And they emit with the light which is allowed by their own orbitals around the nucleus. Yeah. So they can only move in very well specified frequency, from move up or down depending whether they're excited or de-excited. Yeah. So we have an imprint. It's like a fingerprint. So we really have a fingerprint for each single star. And that's also what tells us whether the stars are going away from us or coming toward us. Because once we know the fingerprint, we can see whether it's blue shifted or red shifted.
Mm-hmm.
If it's blue shifted, the star is going away from us. If it's red-shifted, the star is coming at us. So actually, we can even.
I thought red-shifted was getting away from.
Sorry,
us.
red-shifted going away.
Blue is coming and red is moving
sorry,
away.
the other way around. Red-shifted, they're actually moving away, and blue-shifted, they're coming at us.
Because I heard about that before, described as the Doppler effect. If you're hearing an ambulance coming, you can hear a different pitch as the ambulance comes towards you and then moves away again.
Exactly. So the pitch is higher if it comes toward you, and is actually smaller if it goes away from you. This is the pitch of light. Yeah. You can also do that. So you really can. That is the way we as humans have learned about the universe. Yeah. So when we understood how the atoms worked, then we actually could basically use that information to look at the rest of the realm around us.
So we're talking about light here, and light. It's. I would say it's okay for me to get my head around. Mm-hmm. It's because we're talking about a spectrum of light here, and all the colors we see is part of it, just a very small part of that. At one end it goes up to X-rays and gamma rays, and at one end it goes down to radio waves, so it's all to do with the wavelength of these, of the electromagnetic spectrum.
Exactly.
So light, I think I've got, but the magnetism part of it, how does that come into? Basically, what I'm saying is I can't really understand magnetism.
I don't think. I mean, electron and magnetism actually became the same force, right? So, and again, it's due to relativity again, right? So you can have an electron which creates an electric field around it, or you can move an electron, and then start auto creating a magnetic field. So in a way, these two forces are complementary to each other. It depends also the way the things move. And so electromagnetism are an expression of the same force, right? So the electric and magnetic field are actually expression of the same equations, so-called Maxwell equations. And it was breakthrough really when people started understanding that indeed they were related. They were not two different things. They were expression of the same force. Mm. So one way to think about it is that you don't have to think really about it, about electro and magnetism, right? It goes back to because we have historical heritage to have experimented them differently, but actually they all come from the same force, with its electromagnetism.
It's amazing that we take it for granted. It's how we get power. It's how we do our telephones have power. It's how we make electricity. Yes. But it's as you said, you're not meant to understand it.
Meant to share it. It's like one of my remember teachers at university, when I asked him what is temperature, it's like it's not something you have, it's something you share. So it is really you have to think about a force as the mediator that of interactions in between particles, right? And that is actually what really the electromagnetism is. It's the mediator of the electromagnetic force between two objects that experiment the electromagnetic force. We have also particles that at first instance don't experiment the electromagnetic force. They are neutral. Right? So, but they will actually eventually through so-called quantum corrections fill them in any case. But I mean, at the first instance, they actually are transparent to light.
Well, let's take the universe. They come from stars.
Yes.
Which is incredible.
Yes.
So, and stars are made from protons, hydrogen.
Yes, exactly.
So,
where did they come from? Yeah, it's a good question. I mean, we don't know where the protons came from. The meaning of that is that if I ask the simple question, why there is something rather than nothing, the answer is actually we don't know. What all the fundamental forces that we have so far, if you ask them, could you explain why we have protons rather than just pure energy around us? Actually, the prediction from what is called the standard model is that we should have pure energy. As the universe is, I mean, assuming the universe were democratic at the beginning, and it had created the same amount of matter and antimatter, stuff and anti-stuff. And we know there exists the anti-stuff. And you ask, you run the movie of the universe, according to the laws of physics we know now, you will find out that nowadays we shouldn't exist. Which means the laws of nature we have now are wrong, or at least partially incorrect. because they can't even explain why we have protons and not an equal amount of proton and antiproton that annihilated away into pure energy. So this is one of the big mysteries right now, right? Why there is something rather than nothing. Now, your question is where the proton come from in the first place, right? As I said, I can't tell you. And if you know the answer, don't tell me. Write a paper, okay? So I cannot tell you why we have protons rather than nothing, but I can tell you what a proton is made of, which is a different answer to the question asking. Right? The proton is actually a bag full of glue.
Right? Bag full of glue.
Yes, and it's actually very accurate.
Yeah.
So this, you typically hear the story: the proton is made by three quarks. Three quarks are bound together by a strong force. The strong force provides the glue between these three quarks. And here we go, we have a proton. But if I ask you, all right, put a proton on a scale, weigh it, would that be equal to the sum of the three parts? The answer is no. You will get that if the most of the proton mass comes from the interactions, not from the constituents, right? So from sometimes lighter, you can consider the electron to be technically irrelevant for the mass of the urbanars. But as I told you, each single proton mass comes from the interactions that keeps the proton together. So that is maybe one of the most famous examples where mass comes entirely from the interactions, or most of it, over 90% comes from that. And that is actually experimenting equal to MC square in the most beautiful of the ways, right?
So by interactions, you're not talking about us clinking our glasses?
No. Yeah, that's also. I mean, that's an interaction. Effectively, it has also weight, but it's tiny compared to the weight you have in the protons that makes your glass. Yes, an interaction has a mass. I mean, you can actually transform into a mass. If I raise my glass, right, there is a potential energy, right? If I let my hand go, you will kill me because the glass will fall and smash on the floor and the beer will be all over the place. There is a potential energy provided by the gravitational field which is around us. And this will fall back. So there is potential energy, and this energy can be actually identified with a mass.
So as you raise this glass higher from the table, you're very gradually or almost insignificantly changing its mass.
Yes, I mean, in fact, it's maybe a most famous example of that. If I ask you, how long does a neutron lives? What would be your answer? So if I take an atom, and we know 8 atoms are stable. Now let me take a neutron out of the hydrogen atom and put it on the table. How long will it last? 15 minutes.
15
minutes. Within after 15 minutes, the neutron will disintegrate itself into a proton, an electron, and a neutrino of the electron. Now the question is, how come it doesn't disintegrate inside the atom? Why are you still here? I mean, we've been speaking for more than 15 minutes and I haven't seen you disintegrating away.
Yeah.
So something is keeping the neutron from disintegrating itself. What is that?
Just a couple of questions there. So how long would a proton live if we were to set it? Forever. Okay.
Or as longer, we have already measured that, it lives longer than the age of the universe, which is roughly 10 to the 32 years.
Wow. And so whenever this neutron decays into a proton, an electron, and
a neutrino,
what would be would the sum of those masses equal to the sum of the neutron?
So the mass of the neutron is 1 million electron volts heavier than the proton. The mass of the electron is half of a million of electron volts. So there is enough, so-called in physics, phase space or available for the neutron to decay into a proton and give half of the energy to the half of a mega electron volt to the electron and the rest to the neutrino. So why does it not happen in the atom? When it is in the atom, then actually there is a so-called binding energy, a potential energy that actually shifts the mass of the neutron by exactly half, a little bit more than half mega electron volts to make it impossible for the neutron to decay in smaller parts. And that is the potential energy that saves us from collapse.
The interactions.
Yeah, we wouldn't be here talking were not for that. Imagine that, how sensitive the entire life is. So when people say they want to understand how life works, if you don't understand fundamental interactions, what are we talking about? Right. So if you imagine, without knowing Einstein's theory of relativity, if we will not be able to understand this, the nuclear forces, the electromagnetic forces, life wouldn't exist at all. We would not be here.
What's really incredible is that as a species, we've only figured this out 100 years ago.
Yes.
It's a couple of generations ago.
Exactly. And we also know when to quit Earth, right? Because we also learn when the sun will go off. So as I used to say to my students in classical mechanics, you should keep dear to you a physicist and an engineer. The physicist will tell you when to quit Earth. The engineer will make the spaceship. So make sure that you have them as friends.
How long do we have before we have to get off?
Fortunately, we can be okay. I mean, maybe we'll kill ourselves long before the sun does that. But eventually we are doomed. We cannot keep the sun from collapsing.
Yeah.
So that to me is amazing when we kill each other. We do, when effectively we live already on borrowed time.
Yeah.
So all we should think of is how to do time travel, how to do space travel, right?
Time travel?
Sorry, space travel, let's do that.
Okay. Well, let's just top up our classes here before we move on.
Yes. Maybe I should need more beer, it would be great. But I'm sure you've watched Interstellar, right? So.
Oh, yeah.
Wouldn't it be cool if you could actually go through wormholes?
It would. Do wormholes exist?
Not currently. Not according to the current theory of general relativity. Wormholes are non-stable solution of general relativity. However, if an alien coming from outer space comes here tomorrow morning, right, that we know that has gone through a wormhole, we should just, not shake their hands because they're incredibly smarter than us. They probably are not here to make friends, but to colonize us.
Yeah.
Because they've been figuring out to make matter that allows a wormhole to be stable. So they are going to be so much smarter than us.
Yeah. But you think that their intentions would be not friendly?
This I learned from a documentary, right? So it was pretty cool. So, do you remember
the documentary Independence Day?
No. The documentary was about evolution. Like, do you know any species that got smarter than another one that made friends with weaker species?
That's a very good point.
I don't know any of that.
Yeah, evidence suggests that we wiped out the Neanderthals. We're wiping out every other species.
So you either actually eat them or you make them pets. So if you're lucky, we're going to become their pets.
Yeah, we can't even be friends with each other.
No, but imagine
what makes us think that we're going to be able to be friends with a different planet?
Yeah, we would be, especially of low life species, according to their point of view.
Yeah.
So I would run for cover.
Can we bring things the whole way back?
Yes.
To the beginning of time.
Yes.
The Big Bang.
Yes.
So I know you mentioned earlier on about you can see if there's a redshift in the stars are moving away.
Right.
This means that the universe is expanding.
Right.
I'm not going to be able to tell the whole story, but that's one piece of evidence that we have that at one point the universe was a singularity, and then it exploded.
Yes.
And then the quarks came, and then the protons came,
yes,
and then the neutrons came, the elements came, and then we came.
Yes.
What happened in that little bit in between?
If I knew, I wouldn't tell you. I'd write a paper. The truth is that we don't know. The truth is that our laws of physics, when get to that point, break down. So unfortunately, we have an unfinished business. So that's why we still have our jobs, right? So,
yeah.
So we still have to do a lot of stuff, still to understand a lot of physics there. There are speculative ideas on how this came to be. And they're fun to actually entertain and to study and to see right now Also, what are the implications on the physics around us? So there are many possibilities, and from string theory to loop quantum gravity to dynamical triangulations, causal dynamical triangulations to group field theory. So this is just a short list of potential quantum gravity theory that should be, or could be, or maybe they're all wrong, able to explain what happened at the beginning of the time. It could be that as we speak, another universe is expanding and it's actually colliding with our universe, right? So all of this we actually have no idea. In fact, there is a logical possibility that many universes have been bubbling up all the time, and we live only one of those, and the laws of physics in our universe are different from the laws of physics in another universe. Right, so this is actually, we might imagine that there is infinite sea of energy and bubbling universes are coming everywhere up, and we're just in one of those with that specific laws of nature.
Is that theory only in mind, or is there any mathematical evidence to
mathematical evidences? I mean, there are physical evidences, and
there's physical evidence.
No. I didn't say there are physical evidences for that. I say that for evidences, I mean experiments.
Okay.
So mathematics can actually be deceivingly beautiful. In other words, we can have amazing mathematics where things are consistent but are not realized in nature. I mean, classical mechanics was amazing, but it didn't work. We needed quantum mechanics, right? So internal consistency alone is not sufficient to make it a law of nature. So I will say that there are many ideas on how the universe came to be. Many are maybe more compelling than others, but it's hard to say which one of these is actually the correct one. So, for example, right now I'm with a number of very, very bright young students. So we're actually having a lot of fun exploring different theories of quantum gravity, comparing against each other, and trying to see what actually they tell about the theories we see at low energy, which means the theories of the standard model. How can you patch them together, right? In string theory, this started as a name as swampland scenario.
The what scenario?
Swampland
scenario, okay.
So the idea is that, okay, so we don't know, we live in a universe with a standard model, which is we have 4 forces, but we know we need to improve on the standard model because we can't even explain, for example, why we exist.
So I think we just talked about the 4 forces. So electromagnetism, weak force, strong force,
and gravity.
And gravity.
And gravity, yes. But when you want to put them together in a quantum theory, right, then we can actually see whether we can patch them together. There is this romantic idea that there's only one single force and everything come out of that. So string theory is one of these romantic ideas where from a single force everything else comes to be, including gravity.
So a single force regarding, say, what temperature?
No, a single force means really a very basic concept from which everything comes up. For example, if I say that the elementary constituent is not a point but a string, then from the different vibration of the string, I can get all the particles I want, including gravity. Is that clearly a beautiful romantic idea, right? So, because I'm unifying all the particles you've seen in one fundamental object called a string. Now, the string can do many things, right? The string has also... I'm not defending string theory, it should be very clear, but as I used to say, the only way to criticize something is to know it. So, string theory is one of the ways where consistently you can patch up different forces, and you can actually write a consistent theory of quantum gravity. Albeit it also predicts extra dimensions, right? So now you can say that's a bad thing because we've only seen 4 dimensions, or this is a great thing. We are about to discover extra dimensions. Depends how you spin it. So personally, I'm interested in understanding. So a coherent mathematical theory of space-time that also is able to describe the ordinary forces is at the very least, a very nice toy model to explore.
Mhm.
Maybe it's even the theory of everything. Who knows?
A theory of everything. That's the goal.
That's the gold star. Yeah, that's the dream.
Yeah.
Okay? That's the romantic dream behind everything. That I wish I can see God in his eyes, right? And say, okay, fine, I understand what you did, right? I'm not a believer, but certainly the romantic idea of a unique theory of everything from which everything else comes out is appealing.
Mm-hmm. So a theory of everything, so that would be able to describe classical physics like Newton's laws, and then combining that with quantum theory, that would also describe what was the mechanism that set the Big Bang off.
Yes, it would actually, in principle, be able to not only to tell how the Big Bang came to be, but whether we had only one, whether others, whether we actually have different universes. So we might be limited by our instruments, right? Unfortunately, even Democritus, when he thought about the atoms, it took 1,000 years before we saw them. So you can be infinitely smart, but unfortunately, if the instruments are not there to be able to see it, it does not really. We cannot validate the theory.
I'm going to get a bit more philosophical now.
Yeah,
so let's say we have this theory for everything,
Yes.
and a good theory is able to predict what's going to happen. So then we would be able to predict, say, what the evolution of the universe up until now, and then where it's going to go, which would then imply that things that happen within the universe is predetermined.
Well, okay. So let me put it this way: you. Depending on what kind of universe we have, right? Because we're going to have different type of universes. So I don't think you can predict what happens, but you can say what is the gross story of the universe, right? But with a certain probability, say what's going to happen.
Well, even whenever it comes to placing an electron, we can't say exactly where it's going to be. There's going to be a probability.
Right.
Like there's a probability that I'm going to take a drink of beer right now.
Exactly. At a classical level, we can be very precise about that, right? Because, I mean, at the macroscopic level, it's a bit easier to actually say. For example, right now, the universe will expand forever. I mean, according to our laws, the universe actually, and our measurements, right? There is a continuous expansion of the universe. Will become very cold, and everything will die out because unless we hit another universe, that's also expanding at the same time, and it will actually enter in our in collision with our universe. And you will have another bang. So, and the laws of nature will change.
If there were multiple universes and they collide, they wouldn't just merge together. It would be explosive.
Depends. I mean, for example, the people have been studying that in string theory. Again, string theory is, think of it as a toy model for playing different things. People have worked in the possibility of different universes and colliding each other. And the way to think about it is that our universe, right, is 3 space and 1 dimension. Sorry, with 3 space and 1 time. 3 space dimension and 1 time. So you can see that, you can think of it as a membrane that actually, imagine that you have this window behind you, right? This window is a 2-dimensional membrane, and then there is time. But we live in 3 dimensions, right? So you can actually see the membrane, and the beings living on that membrane only see the membrane but nothing else, right? So now you could have another membrane, which is another universe, that is actually impacting on you. So that would be actually an impact. So people have thought, what if at the beginning of the universe, rather than being an explosion, was actually a banging of 2 membranes? Then they will actually provide the sound of the gravitational waves coming from there will be different from the sound of the gravitational wave. By sound is metaphorical sound. Or the gravitational wave coming from an explosion. And so people are searching for these cosmological imprints of whether or not our bang was from 2 membranes colliding or actually an explosion, because that would be different. And so now you can see that how admittedly more speculative ideas can actually turn into experimental tests of this idea.
So either our universe slowly cools and expands into a very boring death,
Yes.
or it can collide with
or with something
another,
else, yeah.
or just something else. Yeah.
I would still pay my mortgage, just make sure that I wouldn't count on that happening tomorrow morning. So,
Yeah.
I don't want to give the wrong impression. So please pay your mortgage.
You worked at CERN, Francesco.
Yes,
Yeah.
and I will go there next year too again. Yeah.
Okay. What's the plans next year?
To have fun with physics, yeah. So I think that's it's hard to predict what one will be working on, but I can definitely say what I'm working now. So from experiments point of view, we have exciting results that they came a few weeks after each other. One from CERN, larger, in particular the experiment called LHCb, Large Hadron Collider Beauty. B stands for beauty. Where they were searching for certain processes, rare processes, and these processes seem to disagree with the standard model, at least at 3 sigma, and they've been actually repeating this experiment for 3, 4, 5 years and consistently disagreeing with the standard model. The technical name of that is violation of Lepton universality, which is a very fancy name to say that the muon behaves differently from the electron. And according to the standard model, the energy at which they do the experiments, the standard model predicts that the muon and the electron should behave in the same way. But they calculated this, a certain decays from beauty mesons made of with a quark beauty.
A quark called beauty?
Quark called beauty, and that beauty will decay into a strange, into a strange quark, an object made of strange quarks, and then 2 muons, but it will also decay into electrons, and you do the ratio of these two, and in the standard model, this ratio should be 1, right, with very large precision. And it turns out to be actually not 1, but 0.8, with some error. This error allows you to say that according to the experiments, they are 97-98% away from the standard model. Mm-hmm. We still have to wait for other experiments to test that. 2 weeks later, Fermilab measures the magnetic moment of the muon. This came also in all news, right? Now, the magnetic moment of the muon, you can think of it as a muon also having a little magnet inside. So what you do, you put it in a magnetic field and make it precess. And you can measure the frequency of precession. Right? And then you can compare it to the predictions in the standard model. Now, this is a little bit more delicate than what I told you was seen at the Large Hadron Collider. So Large Hadron Collider, there is no potential theoretical problem with that. With this one, there are some corrections that are not as precise to be calculated in the standard model as in the case of the Large Hadron Collider. Nevertheless, again, the muon magnetic moment turns out to be different than what you predict in the standard model. Now, it's tantalizing to think that something is there. New forces might actually be there that account for the difference from the muon and the electron. These new forces, now, if you allow me to speculate, right? Mm-hmm. I don't like when something postdicts something, right? It's always nice when at the same time also they solve other problems. So we already know that the standard model fails to explain why we are here in the first place. We also know that the standard model fails to explain dark matter. So maybe these forces are able to now not only account for that, but also to actually take into account of these other explanations that were, in any case, impossible to be derived from the standard model. So maybe we're seeing the first cracks in the standard model, and maybe if that's true, and it will take probably a year or two before this will be consolidated, then in a year and 2 years from now, we will all be doing that.
Mm-hmm. And we mentioned the forces of the standard model, but the standard model also contains a list of particles like the quarks and the leptons and the gluons that make up reality.
Yes.
It's the best we have to describe reality.
Yeah, I think it's not very satisfactory. I mean, if you ask me, I think that's disgusting. I don't like to have 3 copies of the same particle. Like you have electron, muon, and tau. They actually have all the same chemical properties. They actually differ in mass. So they call them families, right? So I mean, families typically can be very good, but if too tight, they're gonna hurt you, right? So the same is with the families. We don't know why there are 3 families, and why there should be 3 and not 5 and not 6 and not 7, right? So we don't really have a good explanation for that. So as somebody said, I mean, we have the electron who ordered the muon, right? So the question is where all this come from? Why do we have 4 forces? Why do we have 3 families of particles, both in terms of the quarks and the electrons, muon, tau, and neutrinos? This actually, I think, that the standard model, you put in by hand. You don't understand it. You use them. An example, we can go back to chemistry, right? Before we understood how to make the atoms, Mendeleev came with a table of elements. At that time, it was a fantastic discovery. It was the fundamental table of particles, right? They were the atoms.
And at the time, okay, this is what the universe is made of.
The universe is going to be made of. And then we realized, wait a second. I mean, but actually there is a much simpler explanations. There are protons, neutrons, electrons, and with these 3, I can make all the atoms. That's a fantastic discovery. And we thought, we made it. Protons and neutrons are the elementary objects together with the electrons, and then all the atoms, bang, are done. And now we say, no, wait a second. Even the proton neutrons are made of something else. And they actually, now we find out that they're even more than just the things that makes the proton and neutron. Of course, the table we have now is much, much smaller than the Mendeleev table. But I think it's still too large, according to my taste.
So of the particles that are in that standard model, which of them are in this glass of beer?
Only the up, down, and electron.
So the quarks only?
Yes. No, they're up, down, and the electron,
Up, down, and the electron. Okay.
Only 2 types of quarks, the up and down. And
up and down.
And
okay, so there's only 3 there.
Yes.
Right.
And of course, there are also the gluons that keep the protons together. And then there is the photon that, the keeps actually, that basically allows you to have the atoms. These are the obvious ones, right? The ones that are there. So this is actually, that's why I say who ordered the muon, right?
So we're zooming in as close as we can get, and this is as close as we can get.
Yes.
But what about that space then in between this stuff, like the space between electrons, the space between all the particles you're talking about? Is that really empty space? If we
space, meaning too. Yeah.
The space between.
The space is never empty. Right.
So what is there?
I mean, it's the space is never empty. So basically, what we say is that, and this goes back to quantum mechanics again, right? So, if you ask what the space is made of, right? So, if at one point in this space we have an electron and a positron forming, as long as they leave for a time, you can't measure it. They're gonna be there. So the thing is that as we speak, I mean, an electron-positron pair, like any other virtual pair, which is sufficiently light enough, will form and close. So what we call the vacuum, it's not really vacuum. It's actually made by virtual pair of quantum mechanical objects.
So what we think is empty space.
Yeah.
These small particles, electrons, and its anti-particle, the positron,
they pop up and
they spring into existence.
And they die again.
And they spring out of existence.
Right, exactly. But for a time for which you can, and there's an uncertainty. The time they leave and the energy they can actually have, they're correlated. So we won't be able to make them. But a black hole can make it. And that is why the black hole actually has a temperature.
Okay, so before we get into black holes, we have to get into something that makes inherent sense to me, but I don't understand it. Gravity.
Yes.
So you mentioned at the start of this about how the interactions with the gluons and the up and down gives the proton its mass with Einstein's theory of relativity.
Yes.
So we have its mass, but mass is different from gravity.
Mass is always part of gravity. So gravity is sensitive to mass. So gravity is differently. If you write down the equation for the Newtonian gravity and the equation for the electromagnetic force, you see that they're actually identical at the classical level. The only difference that we say is that the would-be charge in gravity is the mass. So two objects with equal mass, with two different masses, will always attract each other. there is no negative mass and negative mass, or positive mass and positive mass. There is only one type of mass, and they always attract each other. For the electromagnetic force, even though the force is exactly the same expression at the classical level, we can say two protons don't like each other. They repel each other. But the proton and electron, which have opposite charge, they like each other and they try to attract each other. Gravity, on the other hand, is very, likes everybody. So there is, basically, they always attract each other. And this is just a fact of nature. I mean, so it's not something that, springs out of equations, why we do that. But it is actually a fact. But then, our friend Albert, he actually, little Albert decided, this is a gravity is more like an expression of space-time itself. Gravity bends space-time. So rather than thinking of actually a abstract force, think about the space itself, being changing with if you have mass. So mass modifies the space around you. So like on this sofa, on this couch, your laptop there is modifying the surface there. So if you put a ball around your laptop, it likes to get close to the laptop. So at this point, you interpret gravity as a modification of space-time itself. And that is, if you want, the closest kind of understanding you can get to gravity, where gravity and the mass deform the space around it. And therefore, it makes objects fall into each other gravity. Literally, really like where you were sitting on a sofa and you have two, balls on a sofa, and then eventually the two heavy objects will attract each other and try to get to the same place.
So the mass interacts with the fabric of the universe, space and time.
Exactly.
But I am reminded about another CERN discovery of the Higgs Boson.
Yes.
And I didn't quite get that, but this is another particle that creates a field, a force, in which things with mass interact. Yeah.
Now the question is you're asking is a slightly different one. Where the elementary particle gets their mass from. So we already say that even objects which don't have a mass, through interactions, can actually generate mass. This is one way to get a mass. And this is actually, again, through interactions. So now you're already primed to understand that other interactions can also give a mass, right? So in the case of the glue, it's the interaction, the gluons itself. You don't need a Higgs to give a mass to a proton. That's the beauty of that. So we have a generation of a mass of a proton that comes from pure interactions among massless constituents. And that's mind-blowing, right? Now I'll tell you something else. Now there's another possibility where the mass is generated through the interactions with another state, in this case the Higgs. So now, imagine that this is the Hall of Fame analogy, right? This is something that when physicists were asked by the British ministry, right? Can you explain to us, to human beings, how the Higgs works? And they came up with this explanation. I don't subscribe it as the most beautiful explanation, but it is an explanation, right? It's an analogy. And as an analogy, it's just an analogy. So imagine that Michael, you're very famous for science beer. Everybody loves you. You can get to a room, right? And you work out every day, and you're very thin, and and extremely energetic.
It's good this is a podcast.
Yes, exactly. Yeah. You're not seeing Michael, but I promise you, it's like exactly the way I'm describing it. So, of course, I take a little, a beer for free after this. So, but then he enters into the door, and everybody knows him, and people want to get this autograph. And this universe, which we now call a room, right? Because of his interactions with the rest of the people around him, which now you can think of it as the Higgs field, he will slow down. You cannot go fast, right? Now, the star acquires momentum, and by that it will actually effectively acquire a mass, because the clump of people around you will actually slow you down. On the other hand, if a tax collector comes in, everybody tries to avoid this person, because tax collectors are not, primed to be loved. This person will have a lesser mass, because it will go more, will go through the universe unnoticed. Okay, so the Higgs seems also to have a preference to certain particles. It interacts more, and with other particles interacts less. The standard model does not tell you why that's the case.
That's unfair on the electrons and the photons by calling them tax collectors.
Right. The photon is your tax collector, I mean, effectively. The electron is a quasi-tax collector, and the top is the Michael of the situation. It's the object that gets the heaviest mass of all.
That's a nice analogy for describing the...
Yes, I wish I had invented it. But I'm getting, in fact, a beer. They got a bottle of champagne. So.
There you go.
So,
always the same. So we have gravity now, but I'm really fascinated by black holes, that because gravity it's described as a weak force. You know, it takes something the size of our globe to have a reaction to be able to hold my beer in my glass. Yeah. But a black hole has so much gravity that light can't escape.
Yeah.
So what? I can understand it that if you get a really massive object, it sucks everything in. I'm picturing something that's actually massive, but it's so compact, it's a singularity.
Yeah, but I mean, we don't know what is inside the black hole. So I mean, again, for the same reason why we can't run the history of the universe exactly at the very beginning, but there is a singularity. At the same time, we cannot all the laws of physics or we don't have a theory of quantum gravity, so we can't really get to the interior of the black hole and get basically where there is a singularity. What we can say, however, is that black hole forms, we know they exist, we have seen it, I mean, effectively. And the question is, first of all, how do you see a black hole in the first place? Because it's a black and it's a hole. But we can feel their gravity. Now, black holes are solutions. Now, if you just, as I used to say when I teach physics, there are two modalities. One is actually, being guided by your intuition and the mathematics. The other is what we call the blind mode. You just trust your equations, right? So let's go blind mode. So you take the gravity equation and ask, what are all possible solutions, right? The kind of space-time you can have. And gravity says, we can have this type of space-time that has exactly this behavior, will bend the light around so that light doesn't escape. And now you can say nonsense, or say, well, let me look and see if it's there. So black hole came out like that. I mean, they were predicted from the theory of gravity and said, these are solutions of Einstein gravity, so we can better see if they are stable, which means classically they don't go away. So they should be there. And that's the way people start. And then, of course, the first question to say, yes, but how you see a black hole given that, it's really not something that easy to spot, right? Well, say, but on the other hand, it will act to far away from the black hole, very much like a star. It will just pull things together, and people planets, planetary systems, or other black holes or other objects will go around it. So we could see them from their gravitational pull. So and that's the way we saw it. And then it came up Hawking, right? That made Hawking famous. Say, look, but so far we're discussing classical black hole, right? So what if we marry gravity with quantum mechanics? I'm not quantizing gravity. That's a subtle thing. That's why I can discuss it, right? Yeah. Because if I were really to marry quantum and gravity, I should have a theory of quantum gravity. I won't be describing what happened in internal of a black hole, but I'm going to describe what comes around the black hole. Yep. And that's where I can use both theories well enough to say something intelligent about it, right?
Give it to me.
And actually, so how it works? Hawking goes like, oh, right, fine. According to quantum mechanics, as I told you before, even in empty space, at one point, an electron and a positron will form, and then they will annihilate away again. I won't be able to, see them because they will leave for a short amount of time, so short that I can measure it. But now let's assume that I'm close to a black hole, and an electron and a positron pair forms. But I'm very close to the horizon of the black hole, right? So that one of the two particles is actually now going to be eaten up by the black hole. now by conservation of the energy, the momentum, the other one has to go away. At this point, from any observer outside the black hole, they will see an object that radiates. So the object actually now is not black anymore, it's gray. It starts radiating energy. It actually, and what energy? Its own mass radiates away. So a black hole actually is not a stable object. It will actually radiate away energy.
So this particle that just sprang into existence with its antiparticle didn't exist. So now it lives, this particle stays, it doesn't get annihilated.
No, not anymore.
It goes out into the universe.
Right. So, and it will endow the black hole effectively with a temperature, which is called the Einstein temperature. Sorry, the Hawking temperature.
Mm-hmm.
Yeah. So this actually the Hawking, one of the major discoveries by Hawking was actually to marry in quantum mechanics and general relativity. He did not quantize gravity, but he did actually say what are the implications of having quantum mechanics married to a black hole. Mm-hmm. And became the famous Hawking radiation.
And have we been able to see this?
No, because the radiation is too tiny yet to see it. Yeah. But you can see the stuff that the black hole eats. So the recent images of a black hole were actually if you have a star and a black hole, the star will be eventually material from the star ends up on the black hole. We see actually the image of that.
What about time in a black hole? Is time eaten? Does time exist in a black hole?
Time, I mean, again, as we were saying before, think about having that matter deforms space-time. If matter deforms space-time, it deforms both space and time, right? So time, if you were getting closer to a black hole, right, your time seen from an observer outside actually gets lower. And in fact, in Interstellar, when they get closer to the black hole and they go back home in the mothership, the people on the mothership were older than the people that were on the star close to a black hole. So what happens is actually slows the time compared to observer outside. Unfortunately, you will still live in your reference frame. You still don't feel that. But compared to an observer outside, your age slower than that.
If we were to time travel, we would go close, but not too close to a black hole and experience a bending of our own space-time. And then we could come back to Earth and we would be younger than people that were our same age before we left. Yeah. So that's the way
I wouldn't count on that, but yes.
No.
in terms of doing the space travel anytime soon, but yes, that would be pretty cool. Right? Yeah. And I mean, I used to say to my own kids that, they love, of course, Harry Potter and so forth, so on, that actually that the physics we know leads you to worlds which are much, much more weird than Harry Potter.
Yeah.
And actually, that's actually unfortunate that we don't really kind of make this more fun to actually explore, right?
Yeah. Well, reality, it is quite strange that we can sit here and contemplate these things. As we're drinking this beer that's made from plants that grows from our sun, where life comes from. We're able to drink it. We're able to contemplate the physics that's happening in there. We're able to try to describe the universe. So consciousness is a strange thing.
Well, I don't know where it comes from.
Yeah.
I wish I could define it. Yes.
Yeah.
I mean, isn't that one of the 10 questions of this of the next century?
Yeah.
So, I don't know. I mean, it is a fact that we are beings that reflect upon the universe, right? Mm-hmm. So, as you were saying, if you were, it's amazing that we can do that. Mm-hmm. Given that, if you, were to squeeze the entire history of the universe in a year, we would not been walking this. We would not be walking this earth for longer than a second. Yeah. So, and yet we're trying to now discuss the entire evolution of the universe. Right? It's kind of insane. Yeah.
It's quite hard to get your head around.
Yes. But the moment you do, then you have control over it.
Yeah.
But that's cool.
It's very cool. So, Francesco, how did you get into this? How did you get into physics? And what inspired you?
Yeah, no, cartoons, anime.
Okay.
Yes, it's true. Yeah, in Italy, And anyone hearing this podcast from Italy in the 80s will remember that. We were watching what now are called in a fancy way anime, Japanese cartoons. When I was a kid, were just called Japanese cartoons.
Yeah.
And there was one cartoon called Goldrake, right? And it was this cool men come to Earth to save Earth from aliens, right? But the thing is that the soundtrack at the beginning, which was in Italian, not in Japanese, I wouldn't have been able to understand a word otherwise, were actually singing that this cool guy would actually eat salad of cybernetics and salad of mathematics and read books of cybernetics and knows about photons, physics, and so forth, so on. And I need to know this. So I actually was very much primed at that point that I thought it was cool to do this stuff. I learned later that wasn't exactly according to the cartoons.
But it's funny what influences you in your early life. It's a cartoon that lit that spark.
Yes, and I think it's exciting.
Can I talk about your dad?
Oh, yeah, absolutely.
There we go.
But I mean, if you think about it, there are many more things you can do in life, which is, which I don't think as exciting from my point of view. I mean, I respect everybody, but the idea that I can really enjoy understanding things, it's amazing. It's also selfish, to be fair. I mean, I think I don't do this because I want to save humanity. I do this because I love it.
Well, it's also great that there are people like you out there that are looking into these fundamental questions about what are we doing here? How did we get here? I guess I think it's a very important question to ask. So one of the things you did in your career was to establish the Danish Institute for Advanced Study that I'm doing this season of the podcast with.
Yes.
I know it's an interdisciplinary institute. So you have people from different areas. You have people from the humanities and business and social science and the engineers and the biologists and the physicists all coming together. And my understanding is the idea is to see what happens whenever you put these different minds together.
Right.
So can you tell me about the initial idea? Where did that come from?
Right. So this was in 2009. And then I'd moved here in end of 2007. And by 2009, I was blessed enough to receive fundings for opening up my Center for Theoretical Physics and Cosmology.
CP3-Origins?
CP3, right? And which stands for Center for Cosmology, Particle Physics, Phenomenology. And then the dean at the time and the director asked me, that's great. That's the first time since the NIST board we have another Institute for Theoretical Physics. That's amazing. But Francesco, how can we scale this up to, something exciting for the entire university? We would like to, be strong at the international level. So we needed to create something that it was, first of all, not just UNS, but it was Danish.
Yeah.
And it actually drew from the expertise from a number of researchers, where it should be very clear, I never actually think that it's important to interdisciplinarity is not something that you have to force. It's some things that can happen. And that can happen when you have people around you which come from different backgrounds to whom you talk to and you bump into. So great places are actually places where you can bump into.
Well, I'm a big believer in that. The Science and Beers is not just for fun. It's beers kind of symbolize talking to people, and that's where ideas come from. Mixing.
Right, and actually that is the way I was envisioning the Danish IS, and I think I hope that people involved in that now will keep true to that kind of mission. The mission is to leave free the researchers to do what they're best at and to have fun with that. We don't do research for the money, we do it because it's fun. So if it's a place where fun is the name of the game, then you are going to get outstanding research coming out. I would say that's very, very important. If you remove the fun from the equation, I don't think that actually is more relevant.
I think creative freedom is an important outlet no matter where you are. If you're a musician,
Yes.
an artist, or a scientist,
Yes.
you need that creative freedom to get the ideas.
Yes, I think that is where I really hope that the Danish Institute of Advanced Study will keep actually pushing on, is let people free to explore the research, even if it's unsuccessful. I mean, we often remember the success stories, but they all build on a number of failures.
Multiple failures.
Multiple failures. Einstein failed. Bohr failed many times.
Mm-hmm.
We, of course, don't stress that, but maybe we should stress it a little bit more.
Mm-hmm.
All the failed theories of nature that we had, there are tons of them, and thank God that we have them.
And share your failures so that people can learn
failures.
from them.
I mean, you won't be able to make. I mean, that's true not only in science, but in any endeavor where you want to kind of create something, you have to try to fail, continue fail, but fail better.
Feel better.
Yeah, fail better. That's very important. It means, in other words, you have to learn from your mistakes. And actually, we know that there's only one theory of nature, so we are doomed. There is not. I mean, whatever theory we're working on right now can't be the right one, just because only one is right, right? So, but on the other hand, that actually shapes the real theory of nature for the future. That is very important. So the Danish IS, in a similar manner, is a place where you will like to actually let people free to explore what they have to do and have fun with that.
I think that's a very important thing. I just want to touch on one last thing before we wrap up, because I know you have been doing a little bit of interdisciplinary work yourself. This past year, you're a theoretical physicist looking at the fundamental building blocks of the universe, but you get sidetracked into the pandemic last year, and you were making some models for how COVID-19 was spreading.
Well, actually, for overall infectious disease, and this is actually again born out of curiosity, and it's a fun fact of curiosity, and was born at the Danish IS.
There you go.
That happened because February 2020, we get an email from our institute leaders saying that, you have to postpone all your travel. I was scheduled to speak at MIT. I had to spend a month, at least 2 months at Yale, and postponed by how long? So when I asked, a month, 2 months, 3 months, we have no idea. And so with a colleague of mine, I said, look, maybe we can try to figure it out. After all, it cannot be that complicated, right? And so with Michele della Morte, we said, okay, you know what, Michele, let's look at what's happening in China and in Italy and see if we can get something out of that. And then in doing that, in the process of trying to unravel the data for fun, for curiosity, and for personal, understanding when we can travel again, first of all, it became very clear to us we wouldn't be traveling for years, at least another year for sure. And so that was okay, that's not a question of postponing, that's a question of canceling. That's there's a subtlety there. Second thing is that we started figuring out, that the equations that we needed to use to describe what are known as logistic functions for the epidemiological curves, which are really the infection disease curve, were actually surprisingly close to a type of equations we were using to even describe the Higgs. And so at this point it became interesting for me to understand the beauty behind the pandemics. Now, I know it's a sensitive issue because, pandemics, people dies of it, so I'm very sensitive about that. But, forgive a poor theoretical physicist that loves beauty in nature, and that is nature too, right? So it's not the virus' fault we die. I mean, it's just the way it is. But the equations beneath the diffusion process were actually abiding symmetries related to time dilation. And that actually allowed us to effectively, efficiently encode the diffusion process of the pandemics in extremely simple equations that then allowed us to actually model the entire pandemics across different regions of the world. And after a few papers that we were able to publish, actually very well accepted by the epidemiologists, we came actually to predict the second wave pandemics and how they will evolve, which Nature Research thought it was very important, so they upgraded to international news and became actually very well known, and we got so excited about that that now we're actually even using machine learning and artificial intelligence to actually understand how not only the pandemics works, but how we can put these principles together to have a theory of variants of viruses and how they work. So basically evolutionary genetics, evolutionary infectious disease.
No, you're a biologist.
Yeah, am I a biologist? Okay. I would say that I am a kind of a poor physicist trying to understand some basic stuff, but it's true. We're actually trying to understand stuff that you guys know, I'm sure, better than we do. That's really, really cool.
Well, it's very impressive that you're able to model this. Was it received by policymakers?
Yeah, actually, yeah. It's also policymakers, actually. So I would say a little bit too late because we were a bit. You also have to understand. I mean, it's not easy for policymakers because at one point it's not only science, but also there's politics and there is how the people receive things. I can say that if our results in August 2020 would actually been taken more seriously, not by the scientists, by actually the politicians, we have our colleagues also from France, and most likely if they would have acted upon in August, the disaster that happened in France and from September to December, and also in Italy eventually, and many other European countries, actually could have actually been mitigated more. So this is we knew this was coming, and we also knew the impact of that. And that is, we had to run even a movie for it. So
I watched that movie, and I planned my trips back home to Ireland, from Denmark to Ireland, based on your prediction.
Right.
And I managed to get back home just before it kicked off.
Exactly. And imagine if politicians would have used that more precisely. Now we actually want to, since these diffusion processes are not just realm of epidemiology, but are more general. My hope is that we can extend this analysis not only for infectious disease, but also for social sciences, because there are many things that can be related to similar diffusion processes. And I would say that it's important for me that we understand that both at the microscopic level, with the microscopic models, which the technical name of those are called percolation models. And at the more macroscopic level, with this effective description that we dubbed the epidemiological normalization group. But I truly believe that this actually can be extended beyond epidemiology. And it's something where it's some of the next goal. And now, again, we're also, however, putting together with machine learning, and we're going to have... trying to have a theory of variants that doesn't exist very much. And the reason of that is that we have to understand COVID is the first time where we have so much data, also in terms of sequencing. So we're actually looking at the sequences and so forth. So that that's the first time that a virus has ever been studied in such a detail. Both from the epidemiological point of view, from a virological point of view, and from actually massive data point of view. We even used Google and Apple data for study the movement of people in Europe and in the States.
So if there was a lockdown, were people really
we could
staying
tell,
home? Or
right. For example, we can say that in Denmark, people were not staying home. When it came the lockdown, you could see that people were all in the parks. So the actual mobility constraint, which were maximally felt in Europe, were in Spain and Italy, where people were really staying at home. So in Denmark, actually, you can see that, yes, people were not going to work, but they were mostly going to the park.
You're still meeting up.
Yes, which that actually is the way it was, and you can study that. So we have an immense amount of data right now, and this is... not only theoretical physics, but
Yeah.
and fundamental interactions. But if we can use the same mathematics to kind of explain in a much more efficient way, even epidemiology or applications to kind of away from fundamental interactions, I mean, I love that. Yeah, that's what I signed up for.
Figuring out how the world works.
Exactly.
Unfortunately, COVID is now a part of how the world works, but hopefully those variants aren't anything to worry about. And
but the idea is how to actually prevent, right? So, so the idea is to use this actually for understanding the way you can plan, for example, vaccination strategies. So we studied recently the interplay between multi-wave pandemics in US and the vaccination strategy, and the paper just been published. I mean, just been accepted. It will be coming out in a couple of weeks, and it works really well. So we can see how well US has been doing compared to the disaster that we had in 2020. Yeah, so you can really see how and when have the correct vaccination strategy and how that impacts nations. So I think it's a service in this case for us, for the community.
Yep. Well, Francesco, it's been fantastic talking to you.
It's been my pleasure. Thanks a lot
Thank
for
you
the
very
beer
much.
and for the chat.
Cheers.
Cheers.
Well, I loved talking to Francesco there and tapping into his brain and learning a bit about how the universe works and what we still don't know. I find that fascinating. I hope you enjoyed that. Go back, listen to the other episodes of the season, and tell a friend about the podcast. Share it. Give us a review on whatever you're using to listen to the podcast. And yeah, thanks for listening. Next week, the guest will be Professor Susanna Mandrup, and we're going to be talking about fat. My name is Michael McGee. Cheers to science.